Okay, welcome to Thinking Beyond. Before we get started, I have my usual announcements. And the first is, of course, for those who are in the area, we have our annual lecture, the Beyond annual lecture tomorrow with Peter Turchin. And we hope that everyone who can come at 7 p.m. in Marston Theater. And more information can be found on our website and on social media. And our next Thinking Beyond, which will be the last one of this semester, will be with Howard Weissman, and it will be on April 27th at the usual time. And I apologize for a little bit of confusion with the time change, but it's 6 p.m. Mountain Standard Pacific, and then 9 p.m. Eastern. So those are just the announcements for our upcoming events. And then for tonight's webinar, if you have any questions at all during the talk, please use the Q&A at the bottom of your screen to ask the question. And we will get to those at the end of the hour. So I will go ahead and turn it over to the moderator or I don't know the moderator, but to Paul Davies, who will introduce our speaker.
Thank you, Jessica. Do we have a title for Howard Wiseman's presentation next time?
It was not officially figured out yet, no.
But he's a sort of quantum wizard, so it'll be all sorts of amazing stuff.
Yeah.
But anyway, to tonight, and welcome everybody. So Jim Benford is a very old friend. I won't go through his entire CV. He's led a fascinating life. I guess he would call himself an engineer, but he got a PhD in physics from UC San Diego in 1969. And I think I've got my facts straight. Your twin brother, Greg, was there as well. And wasn't it the case that this was the first class of at UC San Diego to do the PhD program? So before we go on, did I get my facts straight there, Jim?
Correct. And in fact, at that time, it was called UC La Jolla. They should have kept that name.
Right. So you were a trailblazer, one of
Oh, yeah. It was wonderful.
that of that distinguished institution, and
More faculty than students.
it's that's the way to go.
Yeah, there were no undergraduates.
So Jim is like a world expert on beams and microwave and laser beams, and it's taken a particular interest in space propulsion. He edited a book called Starship Century a few years ago. I think I have a chapter in there, and he's been an enthusiast of this particular type of spacecraft propulsion for much of his career, along with doing a lot of other more down-to-earth things. And the reason that this is particularly interesting today is because a month ago, my old friend David Blair from the University of Western Australia was making the case that we will never achieve interstellar travel. Interstellar travel is bunk, I think was the title of that. And so we're very pleased to have Jim with us today to put the other side of the story based upon his own very practical experience working in the industry. So that's all you're going to hear from me, because my colleague Maulik, I think, is going to moderate from here on, but I will be staying with you for most of the rest of the event. So I will keep quiet and over to you. I think straight to you, Jim, if you would take it away.
Okay, let's start with the slides. When I heard David's talk, I realized that he didn't know that for 8 years, a substantial amount of funding went into making Starflight much more technically possible. In fact, it was called the Starshot project, sponsored by Yuri Milner, the billionaire. And we spent $25 million figuring out how to get to the stars in the most effective way. Next slide. You see, it's a long way to the stars. To get out of the solar system, we need at least 100 kilometers per second velocity. Right now, rockets produce about 10 kilometers a second. So we're going to have to go a lot faster. The domain around Earth, next slide, The domain around us within 10 light years, there are a fair number of stars shown here. The closest is Alpha Centauri system, which is actually a triple star. Next slide. And the two nearest, the two big ones are the Alpha Centauri A and B. There's a closer one called Alpha Centauri C, which is a white dwarf, and it's closer, but it's not as interesting. Whereas the two systems you see here are about the same size as our system, and the stars are very much like our sun. But they're only 11 AU's distance apart. That's 1.1 billion miles, which means that they're closely interacting, and therefore the stable regions for orbits for planets are right in the habitable zone of the stars. So it's a very interesting system to study, and it's the closest. So how do we get there? Next slide. And here you see the full scale of velocities from 3 kilometers a second, which is like uh, uh, see the sort of thing we have here on Earth, to the speed of the Earth around the sun around the galaxy, and long to the far right is the speed of light. As you can see, chemical and ion rockets can get you around the solar system, but they've reached their limits already, and they'll never get to the speeds you need to get to the stars. For example, the Voyager spacecraft are leaving at 17 kilometers a second. It'll take 100,000 years to get to the nearest star, and they're not even pointed that way. Nuclear rockets are a real possibility, and we've developed fission rockets 50 years ago, but haven't really employed them. And fusion rockets are still in the future, and as are antimatter rockets. So if you look in the far right-hand corner, you see beam-driven sails. Next slide. And if you look closely, you see they can get up to very close to the speed of light. And a number of us have studied them over the last 40 years and have come up with a number of designs. What I'm going to report to you today is the results of the Starshot project, which spent $25 million figuring out whether that was really a practical approach, because the others, such as the fusion rockets and the Bussard ramjets, are not within reach and are far, far too large and to be practically built by in this century. But the sailcraft, that is, the beam-driven sails, are entirely feasible. So let me explain how that works. Next slide. We can skip this. It's basically the vision is let's make things, let's get out there, because there's so many things to study that we can't study from a distance. Next slide. The Starshot concept is this. You launch, number one there, you launch a rocket which dispenses sails, deploys them, and aligns them with a beam on the Earth. The beam then hits the sail with an intense beam of lasers, accelerates them to very high speed in a matter of minutes. They cruise to nearby stars, like Alpha Centauri, for about 20 years, and fly by, take data, and send it back to Earth. They're flyby missions, just as we did with the planets. The first planetary probes were flybys, then there were orbitals, and then there were landers. So next slide. Here's the basic concept. You use a beam to accelerate a diaphanous sail, a very light sail, with an area of about 10 square meters, 4 or 5 meters across, a mass on the order of the mass of a sugar cube. And the laser beam is invisible. It puts about 100 billion watts on the sail for a duration of 10 minutes, accelerates it to 20% of the speed of light, although these days we tend to think a tenth of the speed of light is the right speed. And in 20 years, it's there. It flies by Alpha Centauri. You can launch another one a week later, and another one after that. So they don't all have to succeed. Next slide. The way it works is that there's a beacon higher than the sail that gives information, data to the laser array on the ground that tells it what the atmospheric turbulence is, so it can correct phases and get a coherent beam from the Earth to the sail, which then is launched by the intense beam striking it. Next slide. Now, that laser array is beyond the present state of the art, although the Starshot program figured out how to build one in principle and built a small demonstrator. But it would be very large, on the order of about a mile across, and would have roughly 100 million lasers arranged so that they operated in phase. Now, phase locking has been a viable concept now for 60, 70 years in the microwave, and we use it in radar and target acquisition all the time. But doing it with lasers is a state-of-the-art development. But perhaps the most significant thing that Starshot did was figure out how to make a very large array coherent. Next slide. This is an intimidating slide because it shows there's a viable approach, but it's really complex. So they had to build a demonstrator to show that this actually works. And you can produce, say, 100 million lasers that act coherently at a kilowatt each, and a power level roughly like your microwave oven, but 100 million of them. Next slide. Now, the Starshot sailcraft is complex and very, very lightweight, driven by a beam, and I'll show you what the issues are with it. Next slide. There are a lot of requirements. First of all, the sail has to stay on the beam while it's being accelerated. So that's called beam riding. The material you use has to have the appropriate, almost perfect reflectivity, little absorption. You can't absorb the energy of the laser beam. It transmits some, but it has to have tensile strength to allow that acceleration to occur. And it has to, of course, be very lightweight. And it has to stay stable on the beam. And part of that is it probably has to spin so as to keep its angular momentum vector correctly oriented, just like bullets spin out of rifles to keep them accurately pointed. And then, of course, there's the laser system, which I've just described. Next slide. That's the previous slide. We'll keep going forward. There. Now, the key thing, go back. The key thing about the lasers is the present state of the art in lasers is too expensive. But fiber lasers and semiconducting lasers are being developed very rapidly for commercial applications, and they're following something like a Moore's law trajectory. And so we think that in the future, a few decades hence, they'll be cheap enough that you can build such a large array. And that is the key cost development that has to occur to make this viable. Next slide. The key issue really, I think, is beam riding and stability. Will the beam and the sail stay together? Now, the beam will jitter a little, and the sail has to be able to dance with it. And that is a key factor that has to be demonstrated, but we think we found solutions for it. Basically, the first thing you think of is a conical, concave shape, like a cone, that would have a restoring force so that it would naturally ride the beam. That, I think, will work, but there are other things that'll work too. Next slide. The reason it would work, because a sail that has a payload below it, and this is a parachute with a load, is inherently stable because the center of force is above the center of mass. And that will make it stable as it does for parachutes. Next slide. But there are other ways to do it. If you use an utterly flat reflector, it will fly off the beam in a time scale of about a millisecond. So you can't stabilize it. A concave reflector, like I just showed you, is inherently stable, but there are now diffractive metasurfaces, which are in fact photonic crystals that you can put on the surface, which will uh, control the reflection of the laser beam in such a way that it stays stable. Simulations and calculations say that should be stable, but it has not been proven experimentally, whereas the stability of the concave reflector has been proven by myself 20 years ago. That you can always also use a hollow beam, but you waste most of the beam bouncing. The sail basically bounces off the walls of the beam. That's not very effective. There are also down below, you can see that it has to be strong enough not to crumple, and it shouldn't come apart. So it needs to be spin stabilized to keep it on the beam and in the right direction. Next slide. Now, the craft itself is quite complicated. It's very thin. As you can see on the left, there's an image of the sail at an angle. In the middle, it shows you it's extremely thin with some somewhat thicker parts. And the thick part in the middle is the system which communicates back to Earth. That's the communication system. On the right, you see the scale against that of a standard human being. Fairly large sail, but very, very diaphanous. And building that is a crucial factor. And that's why you'd really like to make it flat and not conical, because flat devices like this, we know how to make, although we have never made any to that scale, to meter scale. But it seems like it's inherently easier than building a conical one with a parabolic cross section. Next slide. When you send data back, you're going to have to receive it here on Earth, and you'll have a receiving aperture that is also on the scale of a kilometer or a mile in diameter to get the photons, collect them when they're sent back. It will take on the order of 10 years to return the data from Alpha Centauri, because the data rate will be like 10 kilobits per second, and you have a lot of photos and field information and everything else per sail. But it seems feasible to build this with existing technology. Next slide. What I've shown you is the concept, and I'll get back to it in a bit. But just to make this real, let me show you an experiment that I did with colleagues 20 to 25 years ago, which showed that this is a credible concept. Here's the apparatus we used at the Jet Propulsion Laboratory, funded by NASA, in which we placed a sail on top of a waveguide and accelerated it vertically in a vacuum chamber. Next slide. Here's the kind of sail we used. It's a cone made of carbon microtruss, which is extremely light. As you can see in the next slide, you can see right through it. Next slide. You can see right through it. I've got a fair number of them here, and its thickness is like a millimeter, but its aerial density is only 8.5 grams in a square meter. And it reflects, in these experiments, microwaves at 90% reflectivity, and 10% went through it. But that was enough to accelerate it very quickly. Next slide. Here's what the microtruss looks like. And it's interesting. You use carbon because carbon sublimes. It has no liquid phase. So it gets extremely hot, close to 3,000 degrees centigrade, before it evaporates. But our sails never got that hot. They got to about 2,500 centigrade, but they didn't evaporate, and they retained their integrity through the flight. Next slide. Here's here's a series of still photographs showing that sail on a flat sail on top of a waveguide at the top, and it is hit by a microwave beam at about a 1,000 watts per square centimeter. And in 30, it lights up because it's absorbing 10% of the energy. But it gets hot, but it doesn't melt. And it starts to lift off. And in the next frame, it's gone. We got up to 13 gravities of acceleration and bounced it off the ceiling of the vacuum chamber 26 years ago. Next slide. Going forward in the future, we want to look at this. Right now, we've done the R&D up till starting in 2016 over a period of 8 years. And the next phase is to do technical demos of this system so as to make credible things like beam riding, especially. And then having built the smaller system, we can do precursor space missions in the solar system at speeds much higher than we have now, so that we could get to the outer solar system in, for example, a year instead of 10 years. Then we build the full Starshot system, begin operations about 2050, and then about 2075, we start getting data back from Alpha Centauri. That's the scheme. Next slide. Here's the scaling. What you do is start with precursors. On the left, you have mass. On the right, you have cost. But this is actually in the units are wrong here. The cost, we think, of a full Starshot system would be about $10 billion a couple of decades from now. And we'll achieve higher and higher velocities until we reach something we can use to get to the stars. Meanwhile, we can explore the outer solar system in flybys, which is all that's done in the outer solar system beyond Saturn so far, and go in the interstellar medium and find out what that's like. Next slide. What we need to do in the future, and phase two, phase one having been completed of Starshot, that's the $25 million we spent in the 8 years. We need to demonstrate beam riding in the laboratory. And this is a concept for what we would do. We do it in vacuum on the ground. So you have to reach above 1G in order to lift off, of course, because we're in a gravity field. And what you try to do is make sure that the beam and the sails stay together, that beam riding can be achieved. So you need a fairly tall vertical chamber to fire the sail upward and make sure that it stays on the beam. And you can try various sail materials, various sail shapes, and fiddle with every detail of it. And that's really the next major experiment we'll need to do. Next slide. So what's the future of this concept? We determined that beam-driven sails are the only way that we can get to the stars in this century, that we can send probes. And the reason we want to send probes is that we can't build telescopes big enough to really resolve much in exoplanets at stellar distances. Notice that we sent the New Horizons spacecraft to Pluto so that we could see it, because even on the Hubble Space Telescope, we couldn't resolve the features at all and didn't know anything about it really until we flew by there 11 years ago. Completion of phase two and demonstrating beam riding and several other things would bring enough credibility that we could then start to do orbital experiments, orbiting sails, hitting them from the ground, showing we can accelerate them from the ground. And so we could realize this dream of interstellar travel. So the hope of doing that lives. The work will go on and into phase two, and that dream may actually happen in the lifetime of some of you. Next slide. If you want to know more about this, there are two online essays about 5,000 words, which give you a lot more information about this and a lot of references and things you can look up that will explain the Starshot project in great detail. There's quite a lot written about it. Uh, and finally, well, next slide. I want to quote my friend Bob Forward, who said long ago, and when he made this whole concept credible, that it's difficult to go to the stars, but it is not impossible. So I'm looking forward to, I hope, the funding of phase two, and we can get on with getting with finding out what the stars really hold, what mysteries can be revealed. Thank you.
Wow, thank you very much for that amazing, exciting talk. Um, I want to invite the audience as usual, submit your questions in the either in the chat or in the Q&A. Yeah, so let's get started. We already have some questions. So our own Roger Windhorst asks, will the laser beams get deflected by the Earth's atmosphere sodium layer, like it does for ground-based?
Well, that's the whole point of the beacon, is to allow us to take out the turbulence on small scales that exist in the atmosphere at visible frequencies. If we were to do it in early times with microwaves or millimeter waves, there isn't such turbulence in the atmosphere, and we wouldn't need that beacon. But for lasers in the visible, we will need to have phase corrections from a distance to make the array fully coherent.
Okay. Matt Homan asks, why not skip the atmospheric problems and put the laser array in orbit or on the moon?
Because it would cost a fortune that probably cannot be afforded in this century. After all, it would weigh 1,000 times what the space station weighs, at least, and not even Elon Musk could afford to put.
Great. Um, then we have a question about the survival ratio. So last month we had a talk by David Blair, who claimed that interstellar travel is impossible. And the argument was that that space has a diffuse sort of gas of
Yeah,
particles, and if you're traveling through these particles at close to the speed of light, then effectively you'll be bombarded by ultra high energy particles, and they'll just
yeah.
blast holes in you. So, what's your take on that?
Well, first of all, they probably told Columbus it was going to be impossible to get across the Atlantic too. Of course, they didn't know how wide it was. It wasn't actually all that wide. The compared to the Pacific. Well, there's a straightforward way to deal with that. You accelerate the sail transverse to the beam, face on, and then once you're through the acceleration, you rotate the sail, which is only on the order of 100 microns thick. And you reduce the cross section by 8 orders of magnitude. And you have it oriented so that there's a bumper in the front that's a little thicker and will absorb a certain amount of particles. But you're going to lose some, just like mariners lose some ships. The- you're going to lose some, but there's another one next week.
Yeah,
And so you get around it by going in at an angle, and you fire a lot of sails. You launch a lot of sails, and you're going to lose some. And you're also going to have to deal with communicating with a number of them simultaneously, because there's going to be a long string of them on the way out to Alpha C.
right. Is there a possibility of deflecting the incoming radiation? Like if it were ions, for example, you could have even a tiny magnetic field would
Yeah, a
probably
tiny
suffice.
magnetic field might be, and there's a V cross B
Yeah,
that will deflect the ionized ones, but then the dust particles wouldn't be deflected.
right. But you could easily ionize them by probably having a tiny electric field.
Right, from a laser or something,
Yeah.
which makes the sail heavier, which makes the sail slower, and defeats the purpose, and means that if you're either going to go slower or you're going to have a more expensive launcher, the beamer.
Right.
So it's a trade-off, and the only way to really deal with that is to start launching and see what happens and see what works.
Yeah. So related to that, there are questions about. So Steve Ruff asks, please describe the thinking about how imaging and communications equipment could be added to the sale and keep the whole thing within the zero point 0.1 grams requirement.
Yeah, well, that is an amazing development because it appears that it's possible to do the imaging without having a lens. And that's a technology I'm not very familiar with, but it seems like microfabrication techniques are allowing us to make very, very, very light cameras that aren't like the cameras we have on our phones at all, and do allow imaging. And in fact, they're thinking about doing that in spacecraft already. But it's one of the technical challenges. The other technical challenge around it about sending the message back is where do you get the energy from? And it's
Yes.
probably a radioactive isotope system in a planar form that we already use for spacecraft in the outer solar system in order to have an energy source to send signals back, as we did on New Horizons, for example, and on some of the other probes that we've sent in the solar system. But it seemed the group that worked on that thought that it was credible to do it within the mass limit.
So basically, it'll have a little power source, which will be this
Small
radioactive,
power source.
which will, what's the strength of the
It needs,
amount of,
you need on the order of tens of joules stored.
oh, that's not a lot.
No,
Yeah.
it's not a lot. But on the other hand, the photon return rate is slow. But most people don't realize that New Horizons, where we saw these wonderful photographs of Pluto, it took a year to get all the data back. Even in the solar system, the data return rate is slow if the distances are large.
So Matt Kaplan asks about the 10 kilobit data transmission.
Yeah,
Is that seems high to,
that it is high. It's the upper bound of what is feasible. It'll probably be lower, and therefore it's going to be probably years to get a year for a photograph, something like that. It's probably going to be pretty low transmission rate. Uh, but the study group that worked on that thought that that was kind of an upper bound of what you could do. One of the things we found in working with the whole system was that you really don't want to go as fast as you might like because the explorer oriented people want to go fast, but the data acquisition people want to go slower so you can get more data while you're flying past. After all, if you're going past it at a tenth of the speed of light, you have an encounter time that's very short. It's on the order of minutes in the solar system. Now, think that how long does it take light, for example, at the speed of light to get from the sun to the earth? It's 8 minutes, right? And so you have a really short observation time. So that the scaling turns out that you can really make a somewhat heavier spacecraft and go at a lower velocity. And the trade-off is very positive. It goes, essentially, you can get if you the sail if you can if you have take the velocity down by a factor of 2, you can increase the mass by a factor of 16. It's a really steep scaling. And so really, since you're going to start slow at a 1% of the speed of light or something like that, you're going to allow yourself to have a heavier sail anyway, and you get the data back sooner. So as we think now that perhaps something on the order of 5 or 10% of the speed of light is quite adequate and would give us a heavier spacecraft. Not heavy by the scale of today's spacecraft, but heavier than the sugar cube I mentioned.
but if you're going to this other star system at a tenth of the speed of light, wouldn't you need to slow down to take your
Well,
pictures?
you'd certainly
And
like to.
how would
You'd
you do
like
that?
to, but there's no slowing down. Newton's laws, you know. The so what you do is the next sail will get some more data. and the one next a week after that will get some more. And so you have a lot of separate data returns that add up. It's very different from the way we think of spacecraft now. I like the spacecraft we sent out to the nearby planets have been measured in tons, and they take a lot of data, and they don't go very fast. And especially if they go into orbit, you've got lots of time to send data back. But this is a flyby and a very fast flyby. So that's the way you have to live with that factor. The flybys are inherently limited. Remember, the first flyby of Mars gave us a completely incorrect picture of Mars because of what it happened to see flying by.
Um, so I have also a question about what we might hope to learn. We'll get there. There are many questions coming up, including some by David Blair, which we'll get to later on. But
No,
but so of course, one of the exciting things is that our nearest neighbor star system has at least three confirmed planets, if maybe more. So what could we hope to learn about them?
well, the average in stars so far is the average is one planet per star. It might be higher, but we can only see the larger ones or the ones that go across the face of the star. But what can we learn? First of all, you get photos. Everybody loves photos. Um, you get field data, magnetic electric fields. You get particle data. If, as we do on probes now, you can tell, we'll want to know, say, what's the density of the dust particles along the way, and then we can find that out. So, and we can do spectroscopy, not just visual photography. So all the things we do on spacecraft now to examine the planets of our system, we would want to do there.
It still seems like taking a picture while you're flying past at a tenth of the speed of light sounds incredibly difficult. You would need to have an amazing aperture for that, a shutter speed for that. Um,
Yeah, yeah,
in
yeah.
addition to, I don't know,
Escape,
well, I
yeah,
don't know if the image would have
and
relativistic distortions.
very receptive sensors to gather the data. Yeah, true.
Yeah,
Um,
I just want to jump in here because that was actually all of my questions were related to that. But I guess like part of the problem is you'd actually probably have to develop like an entirely new measurement scheme. Like we couldn't actually use any existing telescope technology for these devices.
Well, everything we have now is far too heavy for this
Yeah,
mission.
I know, but even just the kind of measurement you would take, I mean, I just
Yeah, you have to
I have a hard time
re-engineer.
imagining
Right.
everything. Yeah. So it's like
Yeah.
completely different astrophysics with
But you
completely
know,
different
that is the
measurement.
trajectory of technology.
Yeah, of course.
Yeah,
Yeah.
well, for example, think of orbital satellites orbiting the Earth, CubeSats. Nobody thought of a CubeSat 20 years ago. They thought tons, not kilograms. So in fact, everything that's going on in technology is to make things more compact and lower density, a lower mass, and I think that'll continue. Just as if you ask, how can you possibly carry around a phone in your pocket when they're so heavy? 20 years ago, 30 years ago, 40 years ago, it was impossible.
No, yeah, I don't doubt that. And I think like probably I guess like the first pass problem is addressing the engineering concerns and doing like a proof of concept. But I guess I'm wondering at like what stage do you actually start to worry about what kind of measurements you could take influencing the engineering design, or maybe like that's just not even on
Oh,
the horizon yet.
as we discovered in this project for 8 years, you have to look at everything simultaneously.
Yeah, that's what
And
I
you
thought.
have to have a lot of meetings of the working groups because they have to interact and they have to feed constraints to each other because it's a systems problem, not a component problem.
I mean, if this works, this would be absolutely amazing because you could go to Neptune in a matter of hours, right?
Oh yeah. Oh yeah.
Um,
Right. And you could explore all those objects we know out beyond Pluto that we know essentially nothing about. And there are all kinds of things you could do. Because right now we're limited by chemical rockets to where You want to look at Neptune? Well, come back in the 30s. We'll have a craft out there by then. But we've reached the limits of chemical rockets. We're going to have to find ways to get much faster. And I think that actually the next stage is going to be nuclear rockets, both nuclear electric and nuclear thermal, in order to get not only speed, but heavier payloads, more thrust. Right now, uh, you want a lot of thrust, you have to have a very big rocket. Nuclear has a much higher energy density because nuclear rockets will produce a much higher exhaust velocity, so you can go faster, but it also can produce a lot more thrust than chemicals ever do. The energy in nuclear reactions is far, far higher than the energy in chemical reactions.
Sure.
Could I just chip in here, having promised to be quiet? Because I'm struggling to see how I can use the chat channel. I think as a co-host, I can't do it. So I'm going to say it verbally, and it's a bit of a digression. But if this is all feasible, and one day, maybe in the near future, we will be sending at least small objects in large numbers to nearby bodies. Then, if some people believe and hope the universe is teeming with life and there's extraterrestrial civilizations out there. Some of them have been around for millions or even hundreds of millions of years, and they might be doing this on a routine basis. Leads me to the question of technosignatures. We keep coming up with this. So the question is, if other civilizations are doing this stuff, maybe some of these objects are coming our way. Is there a type of technosignature we should look for that is so far sort of outside the scope of the SETI research? So it's a question really about, what do we look for if ET is doing this stuff already?
That's a good question. Well, first of all, if it's going to be anything like what I'm talking about, look for things that are really fast. That's the distinguishing feature. And they will be small and they will be a low mass. And so that's not what we're looking for right now. We tend to look for things like comets, which are the opposite of that. So fast is what you want to look for. Things with a large Doppler signature on the photons you can receive off of it.
So there was a question sent in by Peter Rez asking whether diffusion is a problem. So in these phased arrays, of course, the beam will spread. So, but I guess you're giving it all the energy when it's still relatively close.
Yes. In fact, there's a focusing criteria. You focus a beam, and you really want to hit the sail, the beam to be somewhat just slightly larger than the sail. But then after that, you can keep it on for a while, and as the beam as spreads and is to be larger than the sail. It turns out, if you do the math, that you'll get a multiplication in the velocity. If you leave the beam on, the velocity will increase by a factor that is exactly the square root of 2. In other words, 41% more speed if you leave it on for an hour instead of 10 minutes.
Well, that's great. I mean, it'll save us years in terms of how
Yeah,
long it'll take to
it
get.
would. So keep the beam on, right? Because the smallest part of the cost is not the cost of the laser array. The smallest part of the cost is actually for the electricity to drive the array.
Yeah. I mean, it's only for a short period of time that it's on.
Yes.
Yeah.
And you can do many, many other missions with this array. You
So
could
there's some
orbital debris, for example.
Right. There's some more questions about the communication aspect. Kyle Sewell asks, is there research occurring to utilize quantum entanglement technology for communicating information?
People have talked about that, and it's beyond my understanding. Uh, as quantum entanglement is some kind of deep clue about the universe that I think we don't understand. It probably has to do with phenomena on the scale of the Planck dimension, the Planck energies.
Okay, and then Roger Windhorst asks, can we turn to single photon detectors to, you know?
Yes. In fact, there's quite a lot of work going into what kind of detectors to use. That's not my expertise, so certainly single photon is mostly what you're going to be getting. Of those in that array of receivers, they're going to be counting photons.
Okay. Are there any more questions from the audience? If, yeah, please enter them into the chat now, because if not, we will invite David Blair, who gave this the talk last time, to join in as a panelist, and he wants to say a bit about sails, the properties of sails, and then we can
Yeah.
have a dialogue about that. So I just want
Great.
to leave it open for a minute or so if anybody wants to ask more questions before we change this into a kind of a discussion. Jan Spacek asks, were the effect of dispersed gas modeled? I think he's referring to the fact that this is, that there's stuff on the way to the, there's an interstellar medium and so forth.
Yes. Well, we two aspects of that. First, uh, in order to radiate efficiently, the site that seems most likely to be used for such a beamer to send sails to Alpha Centauri will be in the southern hemisphere in the Atacama Desert of Chile, where you're very high altitude. There's very little absorption in the atmosphere, very low pressure, and the real absorber is usually water molecules, and there's no water in deserts. So that's one thing you do. The other question is what about the interstellar medium? It so happens that the reason that the Bussard ramjet, which I mentioned but dismissed, what doesn't work is that we are in a bubble, a cosmic bubble caused by supernovas in the past, which have made the density of gas in our region of the galaxy very low relative to places closer to the galactic center or in globular clusters. In fact, it's very low density, and that's why you can't use Bussard ramjets, but it also means there's less of a problem hurtling toward the stars.
Okay. I have a question also. Oh, there was a question by Alex Tolley. How is the sail orientation changed so that it can cruise edge on?
Oh, well, there are small propulsion units, very small amount of energy. Remember, there's hardly any mass to move. So you rotate the sail to be head on, and then you rotate it back when you're sending data. And you orient parallel to the direction of travel in order to minimize the cross section against interstellar gas or dust. And there will be some damage. There will.
Right. So I have so we're giving it almost its entire velocity vector right here near Earth, right?
Yeah.
And so how accurately can we aim it? Because if we're even slightly off, we have to.
Yes. That precision in pointing is a limiting factor on the array, and the opposite thing is how accurately does the sail have to point to Earth in order to send data back? And those are limiting factors in the technologies you choose. True. You have a problem in launching with great precision. They're like 10 nanoradians. And you have a lesser requirement in pointing back toward Earth because, of course, Earth is a bigger target, although by the time it's 4 light years away, it's still on the order of tens of nanoradians pointing accuracy,
Hmm.
which
Okay,
is
I think
achievable and it's
it
cheap.
is.
achievable in the space telescopes have that at pointing accuracy.
Wow.
Well, they have to. They're looking at galaxies that are 10 million light years away.
Right. I mean, here there's no no way to adjust, once you fire it in a certain direction.
True. Once it's launched, it's gone.
Yeah.
Therefore, you not only do you need to know how to point accurately, you need to know accurately what you're pointing at, exactly where the star is or is going to be years later.
Well, presumably you want to actually point it at the planets orbiting the stars.
Yes. Right. So I think this drives is one reason to build larger space telescopes so that we can resolve planets and know where they are, because we're going to need that information.
Right.
And once a few sails have come past a given through a given star system, you'll have better information about what's there.
Okay. All right. Well, in the last 10 minutes, we have now David Blair as a panelist. So I'm going to let him take
Hello,
over.
David. Hello.
Hi,
Have a
hi, Jim.
discussion.
I really enjoyed your talk. Thanks for presenting all of that. I just wanted to raise, a few issues. Um, I've spent 40 years building gravitational wave detectors.
Yeah.
And as you know, gravitational wave detectors use mirrors and very high intensity lasers to measure the motions of the mirrors. And when we first detected gravitational waves in 2015,
2015.
well, 20, yeah, 2015 is right.
Right.
We had achieved 20 kilowatts per power in on a roughly sort of 10 centimeter sized, 20 centimeter sized
Mhm.
mirror, but 10 centimeter sized spot. So that's a and that was the limiting factor for detection. And for the last 10 years, we've been working on trying to raise that power level. And these are the very best mirror surfaces that have, ever been created. We call these things super mirrors. We struggled and struggled to make these mirrors better. And now we're running at about 200 kilowatts inside these machines. Uh, um, we have ambition to get to something like 5 megawatts, but
Mm.
nobody knows if we're ever going to achieve that. But the numbers that you're talking about are orders of magnitude beyond this for the purpose of the acceleration.
Yeah.
The power levels we have make our mirrors deflect a few millimeters as pendulums in gravity. But what we're trying to do is not do a few milli G's of acceleration,
Yeah.
but
Right.
50,000 G's or something. So I find that a really scary ambition. Which bothers me. The second one, I'll just raise these points, and the second is, and it was already raised, is the question about the replies and photons, and we're just in the era when, in the microwave regime, we are almost at the point of having photon counting radios. So we have photon
Mhm.
count. We've had photon counting for visible light for a long time, but now we're just about able to achieve photon counting for microwaves,
Yeah.
so that we can then do really simple estimates of how much power we need to be transmitted back to from Alpha Centauri to be able to make a detection with a certain area telescope on
Mhm.
Earth. Whether, and all of those numbers look rather depressing to me. So,
Yeah. Well,
so
let me
I'll leave it with
reply.
you.
Uh, The sail experiments that I did 25 years ago were at 10 kilowatts per square centimeter,
Mm.
higher than you've got in the LIGO, for example, quite a lot
Yeah.
higher power density, and you could get much higher power densities. I've built test facilities that run up to 100 kilowatts a square centimeter in microwave. The other thing is that when you talked about the microwave photons in receiving, remember that the visible light, micron wavelength has a whole lot more energy per photon than microwaves do by about a factor of like 10 to the fifth. So
Of
there's more
course.
energy per photon, and
Mm.
that makes it somewhat easier to detect single photons
Mm.
in the visible as opposed to the microwave.
Well, yeah. So for the detection side, yeah, you're right. But I believe that we will have single photon
Mhm.
microwave
Yeah,
detection pretty soon on the timescales you're talking about. So that that relieves the some of the pressure um, on the transmission from Alpha Centauri because you've got to get enough bits back. You've got to get enough photons back to send a picture or whatever you're going to
yeah.
do.
And that's why you need a large array to detect single photon per unit. Uh, and
Yeah.
that's true. The other factor to go back to the beam intensity on the sail, it's not necessary to reflect 99.999% of it. Some of it can transmit,
Oh
and
no, no,
and
no,
some
no.
of
It
it can
just
be
so it doesn't
absorbed.
get cooked. It just
Yeah.
mustn't be cooked and
Yeah, well,
evaporated.
the
And that is the
key,
problem.
the thing to really reduce is the absorptivity, the absorption, because that'll cook you, right? And the best material for that we've identified is silicon nitride,
Uh,
for that has the right ratio of all the reflectivity, the absorptivity, and the transmissivity, and the availability to re-radiate in the infrared. Uh, that's silicon nitride seems like the best material, although we've identified several others.
Yeah. Well, in gravitational waves, we've been working with silicon nitride and various other coatings, but unfortunately, we always sort of hit limits that there is that we just don't get sufficient materials purity, or we sometimes we don't know what the
Yeah,
reasons are, but we just can't stop the absorption. And the reason we care about the reflectivity is because we don't want the absorption. Um,
right.
because the absorption in our case distorts the mirrors, but in the case of this of the solar sail, it'll evaporate the sail,
Yeah,
and that of course is what you don't want.
right. Yeah,
But
well,
yeah, let me
that's
just add. Sorry, yeah.
yeah, well, that's the way it is with this application. We're up against the limits of materials, and in fact, these materials will be made the equivalent of 3D printing in the future. We're laid down layer by layer, atomic layer by atomic layer, to get it exactly the way we want it. And you can see that coming in the future, but it really is a long, long way to go for most of this.
And the last point was something that Paul raised, and I analysed that in my book, which was if there are lots of civilizations out there sending these probes around the place, apart from these extraordinarily high energy cosmic rays that they will effectively can be all these Starshot probes. Each one is like a cosmic ray with a, I think I worked out the energy is about the same as the energy of the International Space Station in terms of its kinetic energy.
Yeah, well,
And
well, for the cosmic rays, yes, they're extraordinary,
yeah,
and they're produced by
and
extraordinary
so yeah,
events.
so they'd be the most catastrophic cosmic rays we could possibly imagine if one happened to hit the Earth. So, but apart from that, the flashes of light should have been seen in history. Because not all the
Yeah.
light hits the sail. A whole lot of it goes past the sail, and so these things
Yes.
are fantastic interstellar
Yes.
beacons, and
I
so the
think
sky should be flashing in them. And
it
why haven't we seen them?
That's a really good point. I completely agree. And in fact, it's that leakage radiation would be a way of seeing whether other people are using this technology. And I've suggested that the wow signal, which was picked up at Ohio State in 1977, might have been such leakage.
Mm.
It would not occur again because they're pointing at something else now. We just happen to be in the
Yeah.
That's the problem, is recurring. I mean, they're not shooting at us, so they're shooting at something else like a planet, and you will never see it again.
Yeah. Yeah. Well, thank you, Jim, very much for
Thank you,
yeah.
Dan. Right.
Yes, thank you. We're out of time. We could probably go
Okay.
on for another 2 hours.
Yes.
But thank you so much, and we'll see you. We'll see everyone at the next Thinking Beyond in a month.
Yeah.
Bye bye.
Okay.
Thank you.
Bye.